3, 2, 1, go.
Okay, so this is our roller coaster project. I want to point you to the design that we came up with. We're going to put the marble inside of a spring mechanism for the initial force. Then it's going to go through our first feature, which is the 2-foot loop. Then it's going to go to our second feature, which is a ramp. There's going to be a distance X that we're going to calculate, and then it's going to land back on the track on this side. So that is our roller coaster design.
Our group began by measuring the mass of the marble, which will be used throughout these calculations. And then our group thought it was most important to calculate the velocity that would be needed to get around the curve correctly, which you can see our team did here by finding the needed velocity at 0.3. And we used the normal acceleration with the velocity and the rho that we know due to it being a 2-foot circle, and we found our V3 comes out to 5.6745 feet a second.
So then we wanted to find the velocity needed at point 1 directly out of the spring mechanism to actually make it through the loop. So we worked from point 3 backward to point 1 in this section here using energy. You can see we have our kinetic energy for at point 1, kinetic energy at point 2, the potential energy here for the height that we're going up, and then we also incorporated frictional losses as well. And so that's actually over here. We could not solve this equation until we found the friction force acting on the marble as it goes around the track, and then the actual length of the track, and that's this length, the 1-foot length, and then however long this is up to get to point 3. And so we calculated that over here with that 1-foot length, and then we also calculated the length here around the curve. That came out to be about 4.14 feet of contact between point 1 and point 3 as the marble rolls along the track. And then to find the friction, we did a little test. We cut a small piece of track, and then we lifted that track up. We measured the distance. We lifted it until the marble started to roll. And in this way, we could measure the friction coefficient. And so, in doing this test, we actually measured the time it took for the marble to reach the end of the track. We also ran this test, I believe, 6 times and measured the average height here before the ball started to roll. And so we found that came out to be an angle of about 2.6 degrees. We then calculated the acceleration the ball has as it rolls down. You can see that calculation here. It was about 11.3366 inches per second squared of acceleration downwards. Summing forces in the x direction, we were able to come up with this equation to find our friction in this specific setup. The force of friction we came up with was pretty low at 0.0007 pounds force. From this and our normal force calculation here, we found that our friction coefficient was about 0.00049. Taking that, we could plug that back into this equation, giving us this here, and then we finally found our velocity 1 at 12.69 feet per second.
After that, our group wanted to pick out a spring. We picked out a spring initially, and it did not work. And so we were using springs that we could find around the lab and seeing how far we would actually have to pull them back to accomplish our track goal. And doing this, we realized that we only had to pull this spring back 3.5 inches when we would test it on the track. And so we used this knowing that the potential spring energy has to equal the initial kinetic energy coming out at point 1. And we used that 3.5 inches in the delta x to calculate the K value as 2.59 pounds force feet.
So next we wanted to calculate the velocity at 0.5 as the marble comes out of the loop. And 0.5 is right here in the coaster, and so we wanted to find the velocity there. And so we just did another energy balance. Again, incorporating our friction and then the length that the marble's in contact with the track, we came out to a velocity of 12.68 feet per second at 0.5.
And for finding the velocity at 0.6, we used an energy balance, and our team made sure to take into account the angle that it would be lying on, and using the kinetic energy, the potential energy had, and then the friction losses, we were able to calculate the velocity at 0.6. And that came out to 9.81 feet a second.
So finally, we needed to find the distance, or estimate the distance between the two tracks for the marble to make the jump. And so to do that, by finding velocity at 0.6 in this section, we can split that up into the X and Y directions. As you can see here, in the Y direction, the marble's going about 4.386 feet per second. In the X direction, it's going 8.775 feet per second. And so we just did some calculations to find the time it would take to reach that same point as it goes up and comes back down. So that's why the distance between 0.6 and 7 is 0, because we were expecting it to land at the same height in this equation. Plugging everything in, we found that it would take about 0.272 seconds to reach the other side of the track if the track was the same height as this, which is a foot. So then, taking that and looking at the X direction, we could find the distance between the two tracks. We found that to be about 2.39 feet. So coming back over here, this distance here, we estimate to be about 2.39 feet.
All right. So here's the actual track itself. You want to just do a little quick zoom, pan zoom. Perfect. So basically, we took all those concepts, put it down here. So if you want to zoom in on our mechanism, so we did find a random spring. The calculations are not always going to be perfect because we're going to have losses along the way. So as the marble goes through the track, it's going to hit these little bumps. Also, there's a little wiggle in this, so there's going to be some loss there. Hitting this little connection point, there may be some loss. And as the marble comes down, we had some trouble with this connection point as well. Just finishing up here, once it leaves the ramp, there's going to be loss in air resistance. And then hopefully by the time it gets here, we had some problems with the track moving itself, so we had to make sure it got into the actual thing. That would have been better if it was actually going down. But anyways, at the end of it, once it hits the ramp, which you can see is the distance that we actually calculated, it does finish up and then fall down into our little contraption that stops the marble. Hey.